Hello class, welcome back to lesson 9.2. We're going to spend our second of 4 days in this lesson. And you might remember our last lesson, we started graphing on a polar grid. And that lesson wasn't too bad because we first converted the polar equations to rectangular equations, and we were able to see things that we were familiar with. For example, lines and circles are both graphs that we've graphed before and are familiar to us. But you may have noticed that last example I did was something we called a cardioid, and that was brand new to us. And if you look through the notes completely, you may have noticed that the equation for the cardioid wasn't really familiar to us either. So even when we converted it to rectangular coordinates, that wasn't something that we were familiar with. And so that's going to be kind of the theme of today and tomorrow's, or today and the next lesson, is we're going to be graphing some new things that are brand new to us. So our first example is r equals 1 minus sine theta, and this is in our polar equation format. And the book kind of lines out a three-step process for graphing these new polar equations that we're not familiar with. And the end goal is to try to get a nice looking graph on our polar grid. Now, what we did with the cardioid in the last lesson was, our go-to method, ever since middle school for new graphs is to just do input-output. And so if theta is our input and r is our output, we could use those values to just plug into our graph and see what the graph looks like. And we are still going to do that. However, I'm going to give you one other suggestion. The book offers this, and I think it's a great suggestion. In fact, I'm going to ask that you do it in your homework. And so that's going to be part of your homework instructions, is to first check for symmetry. And they lay out two types of symmetry that we're going to check as we graph these today. And one is we're going to check for symmetry over the polar axis. And if I go to my polar grid here, we are familiar with the polar axis. It's the kind of axis like our x-axis, right? So it's the axis that starts at the pole and goes towards the right along where the x-axis would go. We call that our polar axis. And to check for symmetry over the polar axis, we're going to replace theta with negative theta. And you might remember checking for symmetries in the past. We did a lot of this back in first semester. We checked for x-axis symmetry, y-axis symmetry, and symmetry over the origin. And what we decided was when we replaced either the input or the output or whatnot, what we were looking for is to see if the equation was the same value as the original equation. So if after we plug in negative theta, if we get the same thing, that means that it is indeed symmetric. And then we're also going to check for symmetry over a line that acts as the y-axis, but on our polar grid, it's not really the y-axis. Instead, it's the line theta equals pi over 2. And so that would be this line that's kind of right here. And I think I'm going to see if I can maybe dot that line. So something that looks a little bit like this. So we're going to check to see if there's symmetry over the polar axis or like the x-axis or the line theta equals pi over 2, which is kind of like our y-axis. And if we can find out whether there's symmetry or not, then that can really help us because, again, these graphs are brand new to us. We're not really familiar. We're not really sure what these are going to look like. And so if we're able to get 2 points at a time, that's what symmetry does for us, is if you find 1 point, then you have another matching point. And so that can really help us do things more efficiently. Okay, so let's check for symmetry over the polar axis first. And to do that, again, we're just going to replace theta with negative theta. So we'll say r equals 1 minus sine negative theta. And then you might remember from earlier chapters that sine is an odd function. And so what that means is that sine negative theta is the same as negative sine theta. So we could change this to minus negative sine theta. And then 1 minus a negative ends up being plus. And so we get r equals 1 plus sine theta. So since r equals 1 plus sine theta is different than r equals 1 minus sine theta, that's going to suggest that it is not, this graph is not going to be symmetric over the polar axis. Now, I do want to point out the book suggests that if it works, it does show symmetry, but if it doesn't work, it doesn't necessarily mean that there's not symmetry. But for our purposes, I think for all the ones you do today, it will mean that there's not symmetry. And I know that's a little ambiguous and maybe confusing. Maybe we can talk about that later if that changes. But for now, if the value does not return to its original state, the equation that is, we can assume that that's not going to be symmetric. So then for checking over the line theta equals pi over 2, we're going to replace theta with pi minus theta. So we're going to do r equals 1 minus sine. And instead of theta, we're going to plug in theta, pi minus theta. So then when I look at this, I'm like, okay, well, how do we simplify this? How do I find out whether this is the same or not? And so we're going to have to revisit a topic from the past. So you might remember our huge sheet of identities back in chapter 7. We used a lot, and one of those identities can be really helpful. So let me remind you of some of those identities. We had identities for the cosine of a difference, the cosine of a sum, the sine of a difference, the sine of a sum. And so this one is the sine of a difference. And so we're going to use this identity right here. And we're going to replace A is going to be our pi, and B will be our theta. Okay, so I went ahead and plugged that in. So we get r equals 1 minus the quantity sine pi, cosine theta minus cosine pi sine theta. So sine of pi we know is 1. Cosine of pi, actually take that back, that's 0. And cosine of pi is -1. So then we get 1 minus, so 0 times cosine goes away. This is going to be minus, so it's going to be, let's put a 0 in here. And then I get minus, and then -1 times sine theta will be minus a negative will be plus sine theta. So then we end up with r equals 1 minus sine theta. So this one, you'll notice, is the same as the original. And since it's the same as the original, that means it does show symmetry over the line theta equals pi over 2. So I think what I'm going to do before we actually plug in values to our input and output, I'm going to keep this dotted line here. And that's just to remind me that when we start plotting points, that for every point that's, say, like on the right side over here, we're going to have a matching point over here on the left side. So I'm going to keep that there to remind me of that. Okay, so I think we're ready to put some values in here into our table, and we'll use symmetry to help us do that. You'll notice I switched around. I put theta first and r second. I had it the other way around just because when we have like xy coordinates, you know, we put x first and then y, but for these we put r and then theta. But in this case, theta is our input, so maybe it makes more sense to put theta on the left side since we're used to the input being on the left side. But I think I'm going to do that. Either way is really no big deal. So what I would recommend is that you start with some really friendly values. So anytime I'm thinking about my unit circle and I'm plugging in values, I like to pick my quadrantal angles. So those are like our really friendly values, like 0 and pi over 2 and pi, and maybe like 3 pi over 2. Because those are, the reason we choose those is because those are really easy numbers to work with. For example, sine of 0 is 0, so 1 minus 0 is 1. And then pi over 2, sine pi over 2 is 1, so 1 minus 1 is 0. And so we can go ahead and start putting some of these points in our graph. So 0, 1, so my angle 0 is this way along the polar axis. So I'm going to put a point right here at 1. And then I could probably pause for a moment. So I already know what the value of pi is because remember we decided there would be symmetry. over this line, so that means pi is also going to be 1. So without even really working that, and that's kind of the whole reason we do this symmetry checking, is because it'll help us find pairs of points and graph more efficiently. 3 pi over 2, the sign of that is -1, so 1 minus -1 will be 2, so we can go ahead and plot that point. So that's pointing down this direction. So we're still not quite there yet. We need some more values. So, thinking about my unit circle, I think of values like √2/2 and √3/2 and 1/2. To me, 1/2 would be a really nice number to work with. So the angle pi over 6, I believe, has a sine of 1/2. And so I'm going to pick that angle. That's a friendly number. So 1 minus 1/2 will be 1/2. And so if I go to pi over 6 and plug in 1/2, that's going to put me right about here. And again, if we keep using symmetry, that means along the angle 5 pi over 6, I'm also going to have 1/2. And if you want to add that to your table, you certainly can. So I like to, when I fill out my table, I try to put these in pairs so I can, again, just be a little bit more efficient. So both of those give a value of 1/2. And then I'm also thinking negative pi over 6. So if I go backwards, that puts me in the 4th quadrant. That's going to have a sign value of -1/2. So 1 minus -1/2 will be 1.5. And so if I put that one, I'm also thinking that if I go backwards, -5 pi over 6, that one's going to match as far as symmetry goes. So these two both have the same R value of 1.5. So that's going to help me get a few more points in here. So if I go backwards, -pi over 6 and go 1.5, that's going to be right here. And same thing here. If I go to -5 pi over 6 and 1.5, that's going to put me right about here. All right, well, at this point, I feel like I have a clear enough picture of what's going on, so I'm going to try to connect the points and see what it looks like. And as you can see, after I do that, we end up with a pretty similar looking picture that we had yesterday, that last example, or last week, and that was a cardioid. So this is another cardioid, kind of a heart-shaped figure. And one thing that I would encourage you to do when you're finished is, since these are so new to us, is if you have your graphing calculator handy, I would get your graphing calculator out and maybe plug this equation in and see how it looks. And so let's do that together. So for starters, if we're going to use our graphing calculators with polar graphs, we have to change our settings. So we need to change our graphing calculator into polar function. So here's some settings that I would recommend that you try. So if you press the mode button and go to the 4th line down, we first have to change to polar coordinates. And so I'll do that here with you. So if you go down, again, 4 spots. So it says function, parametric, polar, so we need to change that to polar anytime we're graphing polar. And then the 3rd line down, we want to make sure we're in radians. So you may already be there, but if not, switch back to radians. And then you remember when we first used our graphing calculators back the first 9 weeks, we talked about window settings like X max and X min and scale and things like that. And so we're not going to have necessarily the same settings, though. We're going to have a theta show up, since that's part of polar graphing, is having that angle. And so I would recommend that you go to those settings, and here I'll show you what that looks like. So go to window, and then you'll see those settings show up, and then I'm just going to go ahead and plug all those in. All right, so here are the values that I'm going to suggest to you, and now we're ready to plug in the equation. So we'll go to y equals, and you'll notice this time instead of y equals, it says r equals, which is a good thing because that's how our equations are set up. And we're graphing 1 minus sine theta. So I'm going to go ahead and plug that in. And whenever you're ready to plug in your theta, just go to the same button where x would be, and you'll notice You probably haven't really thought about it before, but you'll see there's an X, a T, a theta, and an N there. And so this time when you press that button, a theta will show up and you'll be ready to graph, and hopefully it'll look something similar to what we just graphed. So sorry, I had to pause the video there just for a second because it wasn't graphing like I wanted, and I found my mistake. On this list of settings here, I had a 2 there, and this really should be a 2 pi. So we're setting the theta values from 0 to 2 pi, which makes sense. That's 1 revolution. And so I went ahead and changed that in my graphing calculator, and then it gave me the cardioid shape that I was hoping for. And you'll notice maybe this one goes out a little bit wider than our graph did, but I think our graph is still okay. Um, you know, maybe our graph could be improved if we plotted, another 4 or 5 pairs of points, but for today's purposes, I don't think we need to do that. So I think this checks out okay, and I think we're in good shape. Definitely encourage you to do that. Get out your graphing calculator, use the same settings that I just shared with you, and just take a few minutes, pause the video and plug in each one of these and see how things change. So if you did that, you would have noticed your graphs look a little something like this for each one. And some things that I would maybe point out or notice here is that whenever it's minus sine theta, the cardioid is mostly below the x-axis, but when it's plus sine theta, most of the graph is above. And you'll notice that trend stays true for these as well. So when there is a minus here, it's going to be below, mostly below the x-axis. And when we have a plus, again, it kind of flips and it's mostly above. Also, you'll notice one thing I'd like you to notice is the coefficient for all of these are the same. So like here I have like a 1 and a 1, a 1 and a 1, a 2 and a 2, a 2 and a 2. But you will notice as the that coefficient gets larger, so like as I went from 1 to 2, the entire cardioid got larger. And if you wanted to take more time and try 3s and 4s and things like that, you'll see that it just gets larger and larger and larger. And so this is kind of the form of our cardioid. Let me flip to the next slide and show you what that is more specifically. So anytime we have a polar equation of this form, r equals a plus or minus a sine theta, where a is greater than 0, that's going to graph a cardioid. And what I want you to notice is that this number here and here, they're both the same. So it's only going to be a cardioid if both of these numbers are the same. So it could be a 1 and a 1, it could be a 2 and a 2. Now the plus or minus, that doesn't matter. Again, the plus is going to put it mostly above the x-axis, the minus is going to put it mostly below. But the absolute value of the numbers, maybe I should say, should be the same. So if one's a 1 and the other's a 2, then that's going to graph something else that we're going to see soon. Also, you might be wondering, all the ones we've looked at so far have had a sine here. So what happens if we put a cosine there? Well, here's what happens. We still have a cardioid, but this time, you notice how if I go back to these graphs here, see how it's symmetric over the y-axis or the line pi equals, or sorry, theta equals pi over 2. And so what happens is if we have a cosine instead, it ends up changing to being symmetric over the polar axis. And you might think about why that is, like, how sine is odd and cosine is even, and so those odd even properties are going to change your symmetry. And so cosine will be symmetric over the x-axis or the polar axis, and sine will be symmetric over the line pi over 2. And so the orientation of where that cardioid is, like whether it's kind of like when I look at this, I see this as kind of like up and down, whereas here the cardioid's oriented more left and right. And if it's plus, you'll see that it's mostly to the right of the y-axis or the line pi over 2. And if it's minus, it'll be more on the left side. All right, well, we just spent 20 minutes on the cardioids, so let's take a look at another example. I'm starting to be curious, what happens if these numbers aren't the same? So what if like this is a 2 and this is a 3? So those values are different. So the only way to find out is to do some exploring, and so we'll do that again. So first we're going to check for symmetry. So we'll start with polar axis symmetry. And I'd really like you to do this as part of your homework. So if you could play along, and it takes a little extra time, but again, I think the payoff is worth it because it helps us draw the graph a lot faster once we notice our symmetry. So I'm going to do 3 plus 2 cosine negative theta. And we know that cosine is even, so that means this will just be the same, 3 plus 2 cosine theta. And so since they're the same, that means this time it will be symmetric over the x-axis or the polar axis. So I'm going to put a check there. All right, for symmetry over the line theta equals pi over 2, again, we're going to just replace theta with pi minus theta. And again, we're kind of stuck in that situation where we need to figure out how to simplify this. So let me go back a few slides to this one here. We have the difference, a cosine of a difference. And so that's this slide here. We want to pick this one this time. When we do a cosine of a difference, we're going to do cosine A, cosine B plus sine A, sine B. All right, so I skipped ahead and wrote all that in there for us. So now I have R equals, so cosine pi is going to be -1, and sine pi is 0. And I probably should keep all this in parentheses, so it's 2 times all of that identity. And so now I have 3 plus 2 times -1 times cosine theta, so that'll be negative cosine theta. And then this all cancels out. So then I'm left with R equals 3 minus 2 cosine theta, and that is not the same since it's minus, and so there will not be symmetry over that line. So I'm going to skip ahead to our graph, and since we know that it's symmetric over the polar axis, normally when I draw my polar axis, I do something like this, and I guess I still can, but I think I'm going to put a dotted line along the entire polar axis from left to right. And again, I'm just doing that to remind me that once we start plotting points, that any point that I find up here, I can place a matching point down here. That's going to help us speed things up. So as we go to our table, I would recommend, as before, start with really friendly angle values, our quadrantal angles like 0, pi, pi over 2. Those are going to be really easy to find values for. So for example, the cosine of 0 is 1. And so 3 plus 2 will be 5. And I like to, every time I get a point, I like to go to my polar grid and make a point. So along the angle 0, I'm going to count out to 5. So 2, 3, 4, 5, so way out here. And then since that's on that dotted line, I'm not going to have a partner point to put with it. So I'm just going to go on to pi over 2. And pi over 2, cosine of that is 0. So 3 plus 0 will be 3. So I'm going to do pi over 2 up 3 is going to be right here. Now this one, since it's clearly above this dotted line, I'm going to put its matching point down here. And that's going to be, really all that tells me is that 3 pi over 2 is also 3. So these two kind of go together. So I save a little trouble. I don't have to actually find that value. And then for pi, cosine of pi is -1. So 3 minus 2 will be 1. And so when I go to pi, I'm going to go over 1 unit. So right here. All right, so now we have a few points in place here, but that's not really enough to see the whole picture. So let's pick some more values. So 2 angles I'm going to pick that go together are pi over 3 and negative pi over 3. Since cosine is even, I know those are going to have the same cosine value. And I picked that one also because that's a pretty friendly number of 1/2. Think about your unit circle. I'm trying to avoid that root 3 over 2 or the root 2 over 2 if I can. So this one has a cosine of 1/2. So half of 2 is 1. 3 plus 1 is 4. I know that both of these are going to have a value of 4 because the cosine of negative pi over 3 is also 1/2. And so when I go back to my graph, pi over 3, I'm going to go out 4 units, 1, 2, 3, 4, so out here. And then for negative pi over 3, or which is the same as 5 pi over 3, I'm going to do the same. So then my next 2 points I'm going to focus on are 2 pi over 3 and negative 2 pi over 3. Those have a cosine of negative 1/2, which again is another friendly number. So 2 times negative 1/2 will be negative 1. 3 minus 1 is 2. So both of these will have an R value of 2. So I'm going to go to 2 pi over 3, out 2 units, so here. And then I'm going to do the same thing for 4 pi over 3. So I feel like I'm starting to get a pretty good idea of what this graph's going to look like. If you want more points, you can certainly do more. We may have exhausted all of our friendly points, but we could use something like perhaps pi over 4 and negative pi over 4. Those will go together. We might need our calculators to help us out on that because so I'm going to have like 3 plus 2 times, and the cosine of pi over 4 is root 2 over 2. And so the 2's cancel nicely, and that's going to leave me with 3 plus root 2. So if you grab your calculator and type 3 plus root 2 in, you get something like about 4.4. And so we could estimate and get a point in a pretty good spot given that. And so maybe that's not necessary, but if you're feeling like you've used all your nice points and you need more points, you can always pick something that's a little less nice and just use your calculator to help you out. So since we have those points, let's go ahead and put those in. So pi over 4, I'm going to go out 4.5 units. So it's going to take me a little under 4.5, about right here. And then the same thing for negative pi over 4. So that's going to take me 3, 4.5, a little under a half, right about here. Okay, so I think I'm ready to maybe connect the dots and see what happens. All right, so here's the drawing that I came up with. And you first might be thinking this looks quite a bit like a cardioid. It's close. It's actually not called a cardioid. I think it looks a little bit more circular. It's not a circle either. It's kind of somewhere in between a circle and a cardioid. And we have a special name for this, and it's called a limacon. And a limacon, specifically without an inner loop. And that kind of begs the question is, well, what happens if there is an inner loop? Well, hold on to that thought. We'll get to that soon. And again, you might be saying, well, why can't I just call this a cardioid? And I think the main difference is that the numbers will tell us whether it's a cardioid or not. Sometimes the picture might be so similar that it's kind of hard to tell whether it's a limacon or a cardioid. So the giveaway is if you look at the numbers, to be a limacon, these numbers can't be the same. So you might remember with the cardioid, we had A and A. So now we're going to have A and B. And so if those numbers are different, they're not going to be a cardioid and instead might be a limacon. Also, for it not to have an inner loop, the B value, so the second number that's in front of the cosine, that one has to be greater than 0 but less than A. So essentially, if the A value is greater than the B value, and so kind of like in this example here, we're going to say that it's a limacon without an inner loop. If we reverse that, if the smaller number is in front and the larger number here, then we'll take a look and see what happens shortly. Just as with the cardioid, we can replace cosine with sine and we still get a limacon. The only difference, I'll kind of scroll back and forth here. Just like before with the cardioid, is if there's a cosine, the symmetry is going to be above and below the polar axis or the x-axis. And if it's a sine problem, then the symmetry will be to the left and the right of the line theta equals pi over 2, or the y-axis. The numbers themselves, A and B, will affect how large these figures get. So if you go back up here, like where there's a 3, like obviously if that number becomes a 5 or an 8 or a 10, then these limacons are going to grow larger and larger and larger. But what's important right now is to notice that for the example that we drew, the B value is less than A, so the second number here is smaller than the first number, and if that happens, there will not be an inner loop. So then that begs the question, well, what if the second number is larger than the first number? What happens then? And so that's going to be our last example. I know this video is getting kind of long for only 3 examples, but of course, this is brand new, and there's a lot of things going on here. And there's even more graphs that we're going to look at in the next lesson. So I'm trying to save you and go as slowly as I possibly can, and I'll introduce a few new graphs to you in the next lesson. So anyways, we're going to go through the process one more time. I think I'll speed things up. I'm going to pause the video here and answer these questions and come right back. Okay, so I'm back, and I found that there will be symmetry over the polar axis. So since cosine is even, we end up with the same equation that we started with over here. And over here, using one of those identities again that you could find earlier in the video, we end up with 1 minus 2 cosine theta, which is different. So that tells me that it will not be symmetric, or at least we think it won't be symmetric over that line pi over 2. So that being said, I'm going to go to my graph. Again, as always, we start with our polar axis. And let me switch that. I'm going to make that solid, I think. And then since we're saying symmetry over the polar axis, I'm going to go ahead and just put a dotted line over that entire axis, just to kind of remind us that about that symmetry, and we could use that to help us as we graph. All right, so now I'm going to go ahead and plot some points. So again, I like to start with easy quadrantal values, quadrantal angles. So cosine of 0 is 1, so 1 plus 2 will be 3 here. And I'm going to go ahead and start with that one. So angle of 0 is going to give me 3. That goes right there. Pi over 2, cosine of pi over 2 is 0, so I'm just going to end up with a 1. And so pi over 2 gives me 1, so that's going to put me right here. And then since pi over 2 is 1 and we have symmetry here, that means that 3 pi over 2 should also be 1. And so those two go together. Maybe I could have just put them together on my chart. And then for pi, cosine of pi is -1, so 1 minus 2 will be -1. And so we get pi -1, so this is kind of interesting. This hasn't happened before. So normally we're used to going off towards the left, but since r is negative, we're actually going to go backwards. And so we're going to kind of figure out what that means here in just a few minutes. And it might feel like that's not right, like there shouldn't be 2 points over here, but mathematically it checks out. And so let's hold on to that thought and see what happens. Let's forge ahead. So I think pi over 3 would be another good angle to plug in. Cosine pi over 3 is 1/2. And so half of 2 is 1. 1 plus 1 is 2. And I went ahead and I put negative pi over 3 there with it, since that will have the same cosine value. So we've got 2 for 1 there. So pi over 3 is going to take me to 2. And then negative pi over 3 is also going to go out 2 units. Then I'm going to go with 2 pi over 3 and -2 pi over 3. Those will be good choices as well. Those have a cosine value of -1/2. And so that gives me -1 up here, 1 plus -1. Both of these go together and going to be 0. And so that's just going to put a point right here at the pole. Okay, so I'm looking at this now. I'm still not quite getting a great picture of what's going on here. So I might, maybe I could try some other values. Maybe I could try pi over 6. I know that pi over 6 and negative pi over 6 will be the same. So when I plug in pi over 6, I get √3 over 2 for cosine. So the 2's are going to cancel out here nicely. And then I just get 1 plus √3. So again, I would just grab your calculator, type that in, and you get about 2.7. And now we have a value we can plug in. So pi over 6, 2.7, that's going to take me out here-ish. And then negative pi over 6, same thing, 2.7 is going to take me out here. If we wanted to, maybe we could do a pi over 4. I have a sneaking suspicion it's going to be right about in here. It's not really going to clear anything up for us. So I'm just going to kind of talk you through this. This is a little bit different, but I think you just kind of have to see it. Actually, take that back. I think I'm going to go ahead and see if I can put a couple more points in here that might help me out. So I'm going to go ahead and pick 5 pi over 6. I went ahead and did that for us. 5 pi over 6, the cosine value there is negative root 3 over 2, so you end up with 1 minus root 3, which is about negative 0.73. So watch what happens when I plug those in. So again, these are negative values, and so I'm actually going to go backwards towards 11 pi over 6. I'm going to get a point right in there. And then I'm going to do the same thing for 7 pi over 6. I'm going to go backwards really along pi over 6, and that gives me a point here. And what you'll notice is that ends up giving me a second point along that same radian, pi over 6. And that's okay though, but I think this really kind of clears up what's going to happen when we draw our picture. So when I draw this, I like to start at the pole, and then I'm going to work my way outside in this direction carefully. And at first it might start to look kind of like a cardioid or a limacon, but here's where you want to stop maybe and kind of be careful. So what's going to happen is we actually go back through the pole again, and then we make this little inner loop like this. And so the last example we called a limacon without an inner loop. So this is the counter example to that. This is a limacon with an inner loop. And you can see quite clearly the inner loop that we created on the inside. And so this is what happens when the B term is the larger one. So remember, when A was larger, it did not have the inner loop, but when B is larger, it will have the inner loop. And so when we have a cosine theta, just like before, that's going to be symmetric over the polar axis and be above and below that axis. And if it's a plus B, it'll be kind of hugging on the right side. And if that B term is minus, then it'll be over here on the left side. If the graph is a sine graph, then it'll be symmetric over the line theta equals pi over 2. So it'll be like above the polar axis or below the polar axis, showing that symmetry. Again, notice it's still saying here that the B value is the greater. And so anytime that B value is greater of the two, then it's going to create that inner loop. If it's a plus B value, then it's going to be up here above the polar axis. And if it's a minus B, it'll be down mostly below the polar axis. All right, so I think what I'd like to do is kind of wrap things up. So as you start your homework today, you'll expect to have some cardioids, some limacons without the inner loop, and some with the inner loop. Let me just kind of quickly summarize what you'll be looking for, how to recognize those things. And if you don't recognize them, it's okay. I really, actually, I kind of prefer that today's lesson is still more exploratory. Okay, so what that means is that you're checking for symmetry, you're plugging input and output, and you're plotting points and seeing what the result of all that work is. And so I'd really like you to do that. I guess if you wanted to, you really could use this chart and get to know them really well, start to memorize them. And that maybe is more for like day 3, day 4, we start to notice those things. So today I'd really like to be very exploratory. I would like you to practice graphing them by hand. If you want to use your calculator to check your answers, I think that's a great idea. Or if you want to just play around on your calculator, or maybe get on Desmos or some graphing website and just try some of these equations, plug some numbers in, see what happens when I change this number. How does it affect my graph? When I change this number, what happens? And if you spend a little bit of time doing that, I think you'll come away with a pretty good understanding. So let me just kind of summarize. So actually, dating back to the last lesson, our circle graphs were all in this form here, where it was r equals a sine theta or r equals a cosine theta. So If it's a sine theta, your circle will either be over here or over on the left side. If it's a cosine theta, it'll be above the x-axis or the polar axis or down here. Okay, and again, that all has to do with symmetry. So whenever it's a sine problem, and that's going to be true for all of these, for all four figures, that for a sine problem, it's going to be symmetric over the line, the y-axis, the line theta equals pi over 2. And if it's a cosine problem, it'll be symmetric over the polar axis. And so you'll notice this example here is a cosine problem because of that symmetry. So again, the cardioid, it's different from the circle in that it introduces this coefficient in front that we add, or maybe a constant, I guess is what I should say, not a coefficient. So this A is our coefficient. The one in front is a constant. And so the key is for the cardioid, again, is that these numbers need to be the same number. Okay, and I guess I should say the absolute value is the same. So one could be plus and one could be minus, and that's okay. But the absolute value of that number should be the same. And if that happens, then it'll be a cardioid. Again, if it's cosine, it'll either hug the left side or the right side. If it's a sine problem, it'll be either above or below. And then for the one loop limacon with, so the one loop is out here that does not have the inner loop. That's the case where these numbers are different. So A and B are not the same. So A does not equal B. I think that's important to recognize. And if A is the larger of the two numbers, so if that front constant is larger, that's going to mean that it does not have an inner loop. And same goes before. This is going to be this graph that you can see here is a sine one because it's symmetric over the y-axis. And so the sine ones will be either up above or below. The cosine ones will be right or left. And then over here, if we kind of flip-flop and say that B is the larger one, that's going to create that inner loop. And again, A still can't be equal to B in this case. So if they're not equal to each other and B is the larger of the two, then it's going to create that inner loop. And this looks like a cosine problem. So cosine will either be over here or over here. And then the sine ones will either be up here or down below. And then here they all are just together once more, so you can kind of see the difference or see them all together in one slide. So I'm going to kind of start in this bottom right corner. So here's again our circle. There's no number that we're adding or subtracting. If we add a number that's less than this coefficient, that gives you the inner loop. And then once it becomes the same, that gives us our cardioid. So you can kind of see the progression as we're going this direction. So this way. And then as it becomes larger, we have a limacon without an inner loop. And then I guess what I'm trying to show you here, even though these are similar examples, these last two, is the larger or the further away this number gets from this number 1 here, the more and more it's going to kind of start to where that cusp is what we call it. So like right here, we call that a cusp. And the larger that number gets, or maybe not the larger this number gets, but the further away it gets from the coefficient in front of the cosine, the less pronounced that little bump or that cusp is going to be. And so that's something that you can kind of look at as well. And again, I would encourage you to grab your graphing calculator, just play around with this yourself, put some numbers in there, and just kind of see how you change numbers, if you change sine to cosine or cosine to sine, how that affects your graph. And if you do that, you're going to come away with a pretty good understanding of this lesson. All right, so I know this was a really long lesson. If you stuck with me the whole way, thank you. I appreciate it. A lot of stuff going on in here. So if you have any questions, please ask. Your book is a great resource too. So if you read through the examples in the book, the book does a great job. Or I'm sure there's all sorts of other videos out there you can find as well. So let me know if you need help, and we'll introduce. We have a few more graphs to show you in the next lesson. So we're getting there. So hang in there and keep up the good work. Actually, before I let you go, I wanted to show you the homework. So go to page 600. I'd like you to do 40 through 50 evens. You are going to be graphing again on the polar grid. So hopefully you have a printer at home that you can print some of those out and be able to show that to me when you turn your homework in. And for today, I really would like you to check symmetry. I know that adds an extra step. and certainly slows you down a little bit. But again, I think it's helpful, and I think, again, we need to understand we're still in the exploratory stage. So I'd really like you to go through that process of checking symmetry, which means you're going to have to use those identities that I showed you earlier, which are right here. Okay, so you might need to reference those. It looks like maybe we only use the first one and the third one. Perhaps we won't need to use those other two. So anyways, I'd really like you to do that. Make an input-output table and then graph. I would really ask you to hold off on your graphing calculator until you're done, or if you're just really stuck and you have nowhere else to turn. Okay, but the goal here is to try to do this by hand, and I promise you that if you go through this process and you do it by hand, you're going to come away with a much further understanding than if you just type things in your calculator and zip through this in 10 minutes. Okay, so it just takes a little bit of trial and error and practice to really start to understand how and why all this stuff works the way it does. All right, well, good luck.